Hello and welcome to the second lecture on extraction. So, in the last class what we did, we discussed the challenges involved in extraction, and based on the challenges, so keeping the challenges in mind, we had a small discussion regarding the choice of solvent. Today we will be going for the contacting devices. What is the simplest contacting device? You have maybe a vessel and or a cylindrical tank. In that normally we have a cylindrical tank with a dished bottom, and usually what we do is the depth of the liquid, say this is taken as h, this is generally equal to the diameter of the tank. Now, in this particular tank what do you do? We introduce the two liquids, we introduce the feed and we introduce the solvent, and then they are agitated here. Okay. This agitation, it takes place either by means of an impeller or a propeller, and which is powered by an electric motor, and after this particular they are agitated, naturally what happens, you have given two particular phases here. So, out of these usually one phase gets dispersed as droplets in the other phase. Generally we find that the liquid which has a lower volume fraction among the two, that forms the dispersed phase. If feed is in a lower proportion, that gets dispersed. If the solvent, which is generally the case, is in a lower proportion, then that gets dispersed. Generally we prefer the solvent to get dispersed, so that greater amount of the solute can diffuse from the feed into the solvent, right. So, once then by means of the agitator or the impeller, we stir the two fluids, and naturally the one of the fluids with the lower volume fraction, that gets dispersed, and then the churning goes on, mass transfer happens, and after the extraction has taken place, we stop the operation and we need to separate the two phases, the extract and the raffinate phase. Now, quite often this mixer and the separation, they occur in the same particular tank. This can happen that after the settling, after the mixing is over, the settling happens. It can also happen that after the operation, from here we take the mixture into a gravity settler, and in this particular gravity settler, the two phases, they get separated as per the gravity. This gravity settler, it can be either a vertical or a horizontal tank, and generally we try to ensure that the inlet velocity is not very high, such that there are not a lot of interfacial disturbances which facilitates the separation, right. Now, when we are designing this mixer settler, what are the things that we have to consider? For the mixing part, first thing is, if this is a batch process, then we need to know what will be the volume based on what is the time of contact and the volume of the two. If it is a continuous process, the feed and solvent are entering and the extract and raffinate are being withdrawn out, we need to know the residence time of the mixture in order to effect a proper extraction or a proper separation of the solute from the feed. So, based on this particular time, the dimension of the mixer is decided. And what about the settler? If the settling has to occur here itself, then for the settling we need to consider the droplet size, because for settling what is required, there were a large number of droplets which were formed. All these droplets, they need to coalesce. After coalescing, if the dispersed phase was the lighter phase, then in that case we will have the droplets coalesce and they form a interface on the top. If it is the heavier phase, then it settles down and forms an interface at the bottom. After that, both of them, they are separated out. So, therefore, for the mixing phase, we need to design the total holding capacity, and for a proper mixer, the design of the agitator is very important. These two things we need to consider, and for the settling part, we need to consider the droplet size. Definitely, as I have mentioned, we would not like to go for a very fine droplets, because although it gives a proper mass transfer, they take a very long settling time. The smaller the droplet, the greater is the settling time. So, normally we would like to opt for extraction purpose. We would like to opt for quartz droplets whose sizes are near about 1 millimeter, and based on that the settler is designed. Now, regarding the agitator part, normally as I have told you, we go for a turbine or we go for a propeller. Most common is turbine. Quite naturally it can be used for a wide range of liquid viscosity. Several types of designs are possible. Okay, we can have the pitched blade type where the blades they are inclined at a 45 degrees and they can give both an axial as well as a radial dispersion. We can also have a back sloped or a centrifugal type which is good for handling difficult dispersions, and we can also have a flat radial type which is the case in this particular case where the blades they are connected to a disc. Okay. And when we have a very large depth, then in that case instead of one turbine we can have a number of multiple turbines. Under that case, usually what we find, lowest turbine it is at a height of say d by 3, the turbine at the top it is at a height of d by 3 from the top, and mostly the other turbines they are d to d by 3 and they are equally spaced. Propeller we do not opt very frequently. The only good part about it is that it is cheap, and when we opt, the 3 blades are most common. The other thing also which we need to remember is that whenever we are churning a liquid, quite naturally vortices are formed. We would like to eliminate the vortices. Now, if we have to eliminate the vortices, what we have? We have the baffles. What are these baffles? They are thin strips of metals which are fastened on or welded on the tank wall. Generally, we go for not more than 4 baffles. We have found that 4 baffles are sufficient. These thin strips of wall, and I will be giving you the design parameters, that they more or less their height is equal to the liquid depth and their thickness is about say d by 10 to d by 12, where d is the diameter. And so these baffles they are more or less equally spaced around the circumference. Usually we have found that 4 baffles are sufficient. So therefore, these baffles are also there in order to eliminate the vorticity part. So therefore, you know that when we are going for a mixer settler device or equipment for extraction, we first need to size the vessel, then we need to design the impeller, and we also need to decide the dimension of the baffles. Let us go one by one. Initially, suppose we go for the settling. As I have told you that the settling it is a function of the holding time, the time which is required for the mass transfer. So, therefore, the holding time we can obtain from the mass balance equations. So, in this particular case, if you would like to find the holding time, so therefore, what we think, suppose we introduce the solvent, right. The solvent is S, and maybe the concentration of the solute, the concentration of the solute in the solvent, that is say it is say Ce0, right, and the extract which comes out that has a solute concentration of Ce. The feed comes in, it has a say solute concentration of Cr0. The raffinate it comes out, it has a concentration of Cr. If we assume that the solvent and the feed liquid they are completely immiscible with one another, then and we are expressing these concentrations in terms of solute free bases, then R becomes equal to F, S becomes equal to E, and we find that the concentration it changes in the solvent or in the extract, the concentration changes from Ce0 to Ce. In the raffinate, the concentration changes from Cr0 to Cr, and generally this Ce, this is in equilibrium with Cr, right. So, therefore, if we can assume an linear equilibrium curve, under that condition C star will be equal to mCr. Now, during this holding time, if we can assume that n moles of solute are transferred in time t from the raffinate R to the extract E, right. So, with this n moles of solute transferred, what happened? The solute concentration in raffinate, it changed from Cr to Cr0 to Cr, and the solute concentration in the extract, that changed from Ce0 to Ce star, I would like to put, because under ideal conditions this is going to be in equilibrium with this. Okay. And I assume that since I have already assumed that the solute free flow rate, it is same for both these solvent as well as the feed. So, therefore, I can assume that the Cr and C star, they are connected by a linear equilibrium curve within the operating range, fine. So, under this condition, when we can assume that immiscible extract and raffinate phase and also a linear equilibrium curve, under these conditions, if we write down the mass balance, we are going to get E equals to C star minus Ce0, which is equals to R into Cr0 minus Ce star by m, right. Now, during a differential time t dt, the total amount of solute that has been transferred, that is naturally equal to dCe dt, which is equal to, from mass transfer considerations, KEA Ce star minus Ce. If suppose instead of considering the extract, we would have considered the raffinate, then in that case also we could have written it down and we could have expressed in terms of KRA, etc., etc. Okay. So, therefore, from this particular equation, we find that the rate of transfer of solute from the raffinate to the extract phase, that can be expressed in terms of KEA, which is the overall volumetric mass transfer coefficient based on the overall concentration gradient in the extract phase. So, once we can integrate this, we can separate the variables, we can integrate this particular equation, we get an expression of holding time in terms of this expression. We have obtained it in terms of the extract flow rate, the equilibrium, the slope of the equilibrium curve, then E by R, and the overall mass transfer coefficient, and we have expressed this in terms of a stage efficiency, where the stage efficiency defines the actual amount of solute which has been transferred and the amount of solvent which would have been transferred had equilibrium been obtained under these conditions. So, using this expression, we can find the holding time. From this particular holding time, we can find out once we know the flow rate, we can find the total amount or the minimum amount of volume that has to be provided in this particular tank. Now, here there is something very important that I would like to tell you. See, so for finding the holding time, we need data on the overall volumetric mass transfer coefficient, which demands the data on mass transfer coefficient as well as interfacial area. Now, this is not usually readily available. And again, we have to remember that whatever solvent you take and whatever feed you take, therefore, there will be some amount of contaminant, some amount of surface active agent, something will be there. With every such sort of contamination, the mass transfer coefficient is going to change drastically. So, normally we do not have data on this, and just like I had mentioned in adsorption, in this case also it is the same. Very frequently we generate data on mass transfer and interfacial area from the pilot plant, and then we use some empirical relationships for scaling up. The scaling up is usually done based on geometrical similarity. So, this is one thing that you need to remember whenever we are discussing any sort of extractor. It is very important that we discuss the scale up relationships as well. So, anyhow, so this is the way we find out the holding time. Usually it is important to remember that generally the holding time of 1 to 3 minutes are sufficient. Only when we go for metal extraction, for which mixer settlers are quite often used, due to the extractive reaction, the holding time can be much more larger, about 10 to 15 minutes. Well, once the volume has been decided, so generally we take D equals to H, as a result of which the volume is given by pi by 4 d cube equals to the volume. From once the volume is decided, we can find out the diameter of the column. Once the diameter of the column is fixed, we will be doing a problem, you will find we can find out the height of the vessel. Once the height is decided, then we can go for the impeller design. Usually these are more or less thumb rule types, and more or less the diameter of the impeller, there are some fixed particular ratios for the diameter of the impeller, the width of the impeller, the diameter of the disc, and also the length of the impeller, and the height from the liquid bottom where the impeller is kept. As I have told you that this same H1 is maintained if there are multiple impellers, the top impeller from the liquid interface is also maintained at the same height. The baffle width, it is around, I had mentioned d by 10 to d by 12, it is about d by 8 to d by 12, and generally the gap is also mentioned, and the number of blades that we have, that is equal to 4. So generally we adopt the turbine agitator, and if we adopt the 3 blade propeller agitator also, the design parameters, the geometric parameters are specified in here itself. Well, once we have decided the diameter and the height of the column, we have completely designed the turbine agitator. The next thing that we need to know, as I have already told you, that it is powered by an electric motor. So, therefore, we need to know the power requirement, and we also need to know how good a mixing that it is doing, which we quantify by means of a dimensionless mixing number. Here, please remember that if the agitator demands a higher power, it is not necessary that it will promote a greater amount of mixing. They are not completely related, because it can happen that we have a higher power, a very fine emulsion is forming, but the mixing may not be so very good. So, therefore, if you find that more or less the power requirement and the adequacy of mixing, they are obtained from some empirical relationships which are based on certain dimensionless numbers. For example, the power requirement is obtained from a power number, and the adequacy of mixing is obtained from a dimensionless mixing number, and both of these, they are plotted as a function of the impeller Reynolds number, which is given as a function of the number of blades, the impeller diameter, and the mixer properties of the liquid inside this. Here, if you find in the power number versus REI plot, you will find a number of graphs. These graphs are for different sort of turbine impeller and propeller turbines. Normally, we would be opting for the flat 6 blade open turbine, and so we will be referring to the graph 1. Now, one thing you have to remember, not only in design but everywhere in chemical engineering, if you are going for any empirical correlations, then it is very important that you know the units of each and every parameter that you are using here. So, therefore, you have to remember that when we are plotting this particular graph, this is applicable for a power number where power is expressed in watt, the impeller diameter in m, it is not the number of blades, very sorry, it is the impeller rotational speed, it is in revolutions per second, mixture density kg per meter cube, mixture viscosity kg per meter second. That is, this is all expressed in terms of SI units. Now, if you have to find out the power number, you need to know this rho m and mu m, both for REI as well as for NP. Finding out rho m, it is not very difficult. You can just find it out from the volume fraction of the extract and the raffinate phases. If you know the densities, you can find out the mixture density. Mixture density for any particular mixture, it is not difficult. But finding out a mixture viscosity, it can often be challenging. And that is the reason you will find that here I have expressed mixture viscosity in three different relationships. The first one expresses mixture viscosity in terms of volume fraction of extract and raffinate. The other one expresses it in terms of the hold up of the dispersed phase in the vessel, and the third one expresses the mixture in terms of mole fraction of each component. Depending upon the data which is available, we can select any one of them. Once we have calculated rho m and mu m, we can find out REI. Once we have found out REI, we go to the proper graph, we find out NP. Once we have found out NP, we found out the power required. But remember one thing, the power required which you have found out is the actual amount of power provided per meter cube of the fluid, excluding the losses in motor, speed reducing gears, bearing stuffings, etc. All these losses, they combine to form about 0.3 to 0.4 times the power. So, therefore, from here the power which you are going to find out, the actual power required will be around, the P actual is going to be around 1.3 to 1.4 times. This will give you the actual power which will be required to drive the impeller. Well, regarding the efficacy of mixing, again in this particular case you will find that more or less it is expressed in terms of certain the geometric parameters, and again for all these parameters the SI units have to be maintained. G is expressed in terms of meter per second square, everything else is in meters, and this is in terms of RPS. So, from here also we can find out the T mixing in seconds. Well, one thing regarding the power, I just forgotten to mention, after you have calculated the power, it is important for you to remember certain checks which we do for all design. So, just check up whether the power more or less conforms to this particular value or not. Well, once we have designed, we have selected the vessel, we have designed the impeller, we have calculated the power. Now, generally as I have told you, in order to find out the total volume or to find out the diameter of the column, if you remember, we needed to find out the holding time. To find out the holding time, we needed some idea regarding the mass transfer coefficient and the interfacial area, which is usually not available, as I have told you. So, generally for scale up, what we assume that for the larger vessel and for the smaller vessel, both of them are operated at constant power per unit volume, and then based on geometric similarity, what we do, we assume that even for the larger plant also, it is equal to pi by 4 d plant cube, and for the smaller plant in the pilot plant scale also, it is equal to pi by 4 d pilot cube. So, therefore, if we know this, we know this, then we can find the diameter of the actual plant. Once we know the d plant, as I have told you, usually we assume this to be equal to the height of the vessel in the actual plant. Once we have done it, then we come to the impeller design. More or less the impeller design is that di, it scales as d, and the RPS, the revolutions, they scale in this particular by this particular relationship, and when we have fully developed turbulence, the power, it can be scaled. If you see, if the power number is the same, then the power can be scaled as Ni cube. And the T mixing, again from here, if you can see, the T mixing scales by this relationship with the impeller diameter. So, therefore, this completes the entire discussion on the design of a mixer settler design. We have just considered the mixer part. If the settler has to be there, as I have told you, the settler has to be designed, or the time has to be decided based on the time of settling or the time of rise of the dispersed droplets to form a separate phase. Now, whatever I have discussed, we would like to go for an illustration problem in order to demonstrate the design of the mixer settler that I have told you. What do I have here? I have got a toluene acetic acid mixture. It contains 250 liters acetic acid and say 62.5 liters of toluene. Now, generally this does not look very good, that 62.5 liters etc. I will tell you the genesis of the problem. The genesis is, very frequently what we do, we use toluene and we perform its catalytic oxidation to obtain benzoic acid, and for this particular reaction the toluene, it is dissolved in acetic acid and cobalt acetate is taken as the catalyst. So, what we did, we started with 250 liters of toluene and 250 liters of acetic acid. The reaction occurred and about 75% conversion of toluene took place. So, then we were left up with a benzoic acid, the unreacted toluene and the acetic acid. This was cooled by putting it in cold water. The benzoic acid crystals they separate out, and we have this particular the mixture where we have toluene. As I have told you, 75% is reacted. So, the remaining amount of toluene is 62.5 liters and it has 250 liters of acetic acid. So, therefore, we would like to separate the acetic acid from the toluene, so that this toluene can be reused again. What do? We know that acetic acid is highly soluble in water. So, therefore, we add water to this mixture and we try to separate acetic acid. There is something that you have to remember before you are going to do this problem. These are practical aspects which you need to remember. Water and acetic acid, it forms an azeotrope at 80% weight per weight of acetic acid. So, you have to remember that when you are using water for extracting acetic acid, the amount of acetic acid extracted has to be greater than 80% weight to weight. Accordingly, we have to design the extractor such that in the solvent recovery, when the extract and the raffinate they come to the solvent recovery unit, the water contains at least 80% weight to weight of acetic acid. How do we go about the problem? All the input data etc. are given. So, you have this comprises of the feed and you are going to give water here for doing. How much water will you give? We have seen that I will show you the equilibrium data. If you see, you will find that more or less toluene and water, they are practically immiscible. So, therefore, I have not drawn it here. If you can represent the equilibrium data in terms of mole ratios, where you already know the mole ratio is defined by this, the mole ratio of acetic acid in the toluene and the extract phase, in the toluene and the water phase, you will get a linear graph with m equals to 16.719. So, for this case we get a linear operating curve, and as a result we find that we can use the Kremser equation, if you remember, which was discussed with you in the class of absorption. We will also be going into some discussions on it. We can use this particular Kremser equation. There it was defined in terms of an absorption factor, which we replace by means of an extraction factor here, and naturally the extraction factor, it is the slope of the operating to the the equilibrium, it is the slope of the equilibrium line to the operating line. So, what we do, we use this particular equation to find out epsilon. This is once it simplified for n equals to 1, we get this. Once we know epsilon, we know this epsilon, what is this? This is equal to the slope of the equilibrium line. The slope I had already mentioned, it is 16.719 divided by the slope of the operating curve. What is the slope of the operating curve? It is naturally equal to S prime by F prime, where both of this is the moles water and this is the moles toluene. So, we know the moles toluene, so we can find out the moles water from this particular equation. So, then we can find out what is the amount of water which will be required in order to effect the separation, and then we can find out whether in the final mixture of water acetic acid, what is the proportion of acetic acid and water, just in order to check that the acetic acid is higher than 80% weight to weight, right. So, from here if we can substitute all the values, see XF, if you can take, you can just find it out. XF is equals to 4.84, the final XR was 0.24, and this becomes 0.24 minus 1 by 16.719, from where we get the extraction factor is 25.56. Then if we substitute it in this particular equation, we know that the total amount of feed that I have already shown you here, the total amount of feed, it is the toluene, it is 54.2 kgs. So, therefore, if you are substituting it here, we get the total amount of water that will be required, S prime, which is nothing but the water in this particular case, that will be around equal to say about 35.5 kgs of water we will be requiring in this particular case. So, therefore, what is the total liquid volume in the vessel in that particular case? The total liquid volume will be 250 liters of acetic acid plus 62.5 liters of toluene plus 35.5, 997 was the density. So, it is around 35.61. So, therefore, this much liters of water. So, totally you get around 350 liters is the total liquid volume, which gives you around 3.35 meter cube of the vessel volume, right. It is actually 348.1, I have just rounded it off. Now, from this if you consider D equals to H, then you get the diameter as 0.76 meters. Based on the quotes, we make it 0.88 meters, or it is equal to 800 millimeters, which also gives you H equals to 800 millimeters. Now, once the vessel dimensions are fixed, then we go for designing the impeller. And for this particular case, we assume say a nice standard 90 RPM flat 6 blade turbine agitator with a disc. For that we have all the data, this is used. So, therefore, we select this particular turbine. For this turbine, we have already mentioned all the geometric parameters, they are already mentioned in this particular case. So, based on that you can calculate DI, you can for D equals to 800 millimeters, you can calculate DI, you will be getting as 320 millimeters, WI you will be getting as 64 millimeters. In this particular way you can keep on calculating number of baffles, that is equal to 4, D disc will be equal to say about 215 millimeters roughly, and then the WB, the width of the baffle will be 80 millimeters. Just I am simply substituting everything in this particular equation. The gap will be around 8 millimeters, etc. So, once you have designed, you know the vessel dimensions, you have designed the impeller. Next, what you need to know? You need to find out the power required. So, from this particular case, you have to find out REI. REI for the present case, you can check up, I have got something like 1.26 into 10 to the power 5. From there, you can find out NP roughly around 5, means it was roughly I found out it was around 5. From there, I found out P. this P was equal to 57 watts, and therefore, the actual power I found out, P actual, that was roughly equal to say around 80 watts. We know that this is quite a low power. So, half horsepower motor would have been sufficient for this, and this is quite expected because the mixture volume is also not high and the system viscosity is also not high. So, therefore, the power requirement is very low, and so therefore, just a half horsepower motor will be sufficient to drive this. Next, we try to find out F mix. Accordingly, we have found out, we have substituted all the parameters, and then from REI we have found out F mix. From F mix we have found out the T mix. We have found out T mix to be roughly equal to 11.8 seconds. You can check it up for yourself. We find that the mixing time is also not very high. So, therefore, the design is fine. Now, if you want to go for a larger scale, quite naturally you will have a larger volume. According to the volume, the diameter of the vessel has to be designed. Once the diameter is designed, the height, the impeller, the power required will be kept the same. So, therefore, everything else can be designed accordingly. So, this was just the simplest type of extractor, which is more or less by a single stage contact we could take it up. We have adopted a single stage contacting device because in this particular case the selectivity of water was very high. So, therefore, single stage was sufficient. For most of the cases we will find that a single stage will not be sufficient, we need multiple stages. Multiple stages can be provided by a number of mixer settlers in series, or more commonly by a continuous operation device, a packed column or a sieve tower. But the design of packed column and sieve tower for extraction and for distillation or absorption are completely different. So, in the next class what we do, we take up the continuous operation devices and we try to find out, or rather we try to discuss how to find out the number of theoretical stages, how to find out the diameter of the column, etc. We will find that the basic theory is the same, but since there are certain intrinsic difficulties or complexities when there are two liquids instead of a vapor liquid mixture, the design equations will be more involved, at the same time slightly more interesting. So, we discuss them in the next class. Thank you so much.